Okay, so it is a pleasure to have here today Dr. Vladimir Airapetian, who is a senior astrophysicist at the NASA Goddard Space Flight Center and also a research professor at the American University, DC, Washington. And he's PI of several missions, NASA Next Project Mission to Young Earth 2.0, NASA Exobiology project on the initiation of life on early Earth and Mars, is PI of one of the cycles of TESS and many other things. And he's an expert on several topics, but in particular on the influence of stellar activity on the space environment and exoplanets and planets, and the connection with life, between life and stellar activity. And so he leads some interdisciplinary activity on these topics. And today, actually, we will address this topic, and we'll talk about the impact and the effect of young solar-like stars on the habitable environments of rocky exoplanets. Thank you.
Thank you very much, Amadeo. So yeah, before I start, I want to thank Amadeo and Francesco for inviting me here. So it's my first time at this university. I'm really happy to be here. It's not my first time in Italy, but first time at your university. And today I'm going to talk about this very delicate, very intricate relationship between us and the sun, and how this, how the understanding this relationship can help us to understand the relationship between habitable exoplanets and their planet-costing stars. And so, and that also will help us to derive strategy to search for habitable exoplanets. So as you can see here, so after my name, you see a number of people who are heliophysicists, astrophysicists, planetary scientists, and earth scientists, and also prebiotic chemists. So this is basically the team that I'm leading to start a conversation. So we started this several years ago to speak the same language, to use the same methodologies and software tools, okay, in order to understand this difficult topic. And when I remember gave one of the first public lectures about this topic, one lady asked me, what this kind of bug is that? This bug. I said, this bug is our planet. This is the Earth with the magnetosphere, with the magnetic shield. And understanding how this bug talks to our sun is very, very important. And that will be actually the subject of my presentation. So the major question that, the major question that we want to ask is that, are we alone in the universe? It's a very ambitious question, of course. And this question starts with the series of the smaller questions, specifically, is life unique to Earth or a common phenomenon in the solar system and the universe? So we want to understand this, what kind of conditions are required to start life and then to sustain life. So the second question is that, is the sun a typical G-type star, and what is role on Earth, Venus, and Mars? So we want to understand the conditions 4 billion years ago when the life started on Earth, whether those conditions are required, because now that we have access to so many different stars, we can basically study the early phases of those stars and find which of them are good parents, which of them are bad parents that can start conditions for important for life and sustaining. And then so the lessons learned for habitability of rocky exoplanets. So as I said, this is the topic of the interdisciplinary studies. That was funded by different NASA programs. And specifically, we have the CECETS, they're called Cellular Exoplanetary Environment Collaboration, the project that was started. NASA Goddard has 4 large divisions. It's the heliophysics division. There's a few hundred people, about 300 people working, studying the sun and the environment in our solar system, planetary environments, astrophysics, planetary science, and earth science. So the our upper management several years ago said that we want to allocate money and we want to create a fifth one. It's the Exoplanetary Collaboration Center. And then Pierce Sellers, the astronaut of British origin, passed away. Actually, he flew twice to the International Space Station. And so we named this program after him. It's a Sellers Exoplanetary Collaboration. So I'm a part of it, one of the person who helped to basically start this program with other people. So basically, I'm going to talk about the coronary winds and eruption from the young suns, solar analogs, and about that what we can learn about coronal mass ejections, solar energy particles, and its impact on the early Earth's chemistry, and also how can we resolve two chemical paradoxes. So it's a paradox, chemical paradox of life, to understand how the biological molecules can be ignited by the processes, by high energy processes, what is required for starting life. And the second question is the faint young-suns paradox, which suggests that our sun was 25% biometrically fainter than it's today. It was 4 billion years ago, and so the life was supposed to be not happening because the Earth was supposed to be an icy ball, but it wasn't. And so, I will end with some very interesting hopes for the, JWST, the one habitable planet that can be found. So I want to start with our galaxy. So that's what we look at our galaxy. We see over 100 billion stars. And so this is the one typical galaxy. And the spiral galaxy, about 3/4 of all galaxies we observe. So of course, and we want to understand, the star that is right here. We want to see that why the sun is, is there anything typical or unique about our sun? So the location of our sun in the galaxy. I want to say only a few sentences about it. And Amadeo and Francesco studied this question also, which is very, very important to understand the impact of our, black hole and the processes associated with black hole, specifically, these energetic processes that produce X-ray, extreme UV emission, and also the fast outflows with the astrospheres of exoplanets. And eventually, we want to answer whether, that the competition, when the planet host star can be more important for the, for an exoplanet with respect to the galactic center. Okay, so, but today I'm going to talk about the planet host, because if we understand the planet host, we can basically then better understand that, how they can compete and what is the region of the inner boundary of the galactic zone, the habitable zone. So basically, I want to start with this, movie that shows. This is the movie that was basically created after we got information about over 5,000 exoplanetary systems with the Kepler Space Telescope. This created a revolution in our understanding of exoplanetary systems and then tests. So what you can see here, so far we have discovered, so the planets with different temperatures, with like Earth-like temperatures, all the way to lava planets, 1,250 kelvins. And the planets also have different sizes, from like Mercury size all the way to Jupiter and super Jupiter planets. And the one thing, of course, that we can see that this is our solar system. We see that's a pretty large one. Almost all of them are really compact, meaning that the exoplanetary systems are so small that they can be be within the Mercury, let's say. So that's why it is important to understand whether at these distances the ionizing radiation from planet hosting stars be detrimental or can be positive for the exoplanetary environment. So that's the question of this closing planet. So that's the one typical example. TRAPPIST-1, probably everybody heard about this. The very interesting system of 7 dwarf planets, like Earth-like planets, okay, and a little bit smaller than Earth. And so as you can see that they're all within the radius of Mercury, the closest. It's the farthest one at 0.06 astronomical units. Okay, it's about 15 times closer than we are to the sun, and the closest one is at 0.1. It's 100 times closer. So the 100 times closer, imagine that X-ray and extreme UV emission goes at 1 of the R square. It's 100 square. It's a 10,000 times greater amount of emission that the closest planet receives. And this one receives the, but 36 times less. Sorry, greater. So therefore, we want to know what's going to happen to if we have a Earth-like atmosphere, how long time it needs, to evaporate the atmosphere. So this atmospheric escape is very important, and other processes. But that's the basically introduction to the topic, that they're all closed-in systems. It's not because all of them are closed-in systems. It's a result of the observational selection. It's so hard to find exoplanets, at 1 AU. Probably will be found. We have some direct imaging methodologies and some gravitational lensing but so far we don't have good statistics. But the transit method that people use in Kepler and TESS and other upcoming missions, and there was the JWST will be using the transit method, and also the radial velocity method. The radial velocity method together with transit method allows you to create a little bit a bigger picture about an exoplanet, because it can also provide information about the mass of an exoplanet and also about the size of an exoplanet. So therefore, mass divided by the volume can give us information about the density of exoplanet. So that's how we can distinguish between the rocky exoplanets from the gas giants. So, and because our goal is eventually to find the rocky exoplanets, so this combination of two major methods are important to gain information about surface gravity of an exoplanet. To understand the exoplanetary systems, I want to start with our, magnetic star. It's beautiful star that we just started to look at and understand. Let's imagine that about 30 years ago, we didn't have enough information about this regions called the corona. It's the outermost, hottest region of the sun, heated to up to 4 million kelvins during those active events. And you can see here, and here, you can see those brightest regions called the active regions that are signified by the, regions with the enhanced magnetic flux. And specified by sunspots. Okay, so if you look at this the sun in the visible band, you will see it here like dark patches here and here and some here. But if you look at X-rays, you see enhancement. Okay, so we want to understand how can we decode this information. On the sun, we have the luxury to basically resolve, in optical, believe it or not, all the way to up to now like 35 kilometers resolution. Can you imagine pixel size at a distance of 150 million kilometers? But on the star, on this exoplanetary environments, it's only 1 pixel. So it's basically when I say sun as a star, I would mean that what kind of information we can get. That's one question that I started about 2 years ago asking. So that we have now 11 years of the continuous observations of the sun in X-rays, in extreme UV, in UV, far UV, in optical, magnetic field measurements, the pixel by pixel. What if I can take and integrate the whole sun information, huge volumes of data in 1 pixel? What would I see? And sun as a star, and then take this, let's say, 10 parsecs away. What would help me to decode information about the stars? Because that's the only star that is around us and closest to us, so that we can start with this magnetic active star. So one thing that we observe, so this is the image. So that our sun, as I said, magnetic active star. When I say active means that it shows the magnetic activity. Magnetic activity is manifested in terms of the eruptions. Eruptions normally come in 3 different ways. The first way is, we're going to run the movie, it's so-called flares. Okay, giant flares, which is the process of the explosive energy release in the solar corona. You will see right here the enhancement. See the enhancement here, and then you saw the ejection of the the material here and then here, and then the formation of this. Let me run again of this noise. Some kind of a, you can see here touch you see those particles. So basically speaking, it's not a noise. It is actual particles. What actually happens, you have this region associated with the strong magnetic field that creates, this enhancement, the brightening, the energy released hits the plasma in the corona. And then, due to the magnetic reconnection, part of it ejects with the speed up to 2,500 times per second into outer space. And then when you have an ejection of materials called coronal mass ejection, this coronal mass ejection forms the extended shock waves, and the shock waves accelerate particles to up to 3 giga-electronvolts. So that's the particles that you see here. So this is not noise, it's actual particles registered by the detector. So this image has the 3 different images: the detector image, the LASCO image that basically detects this, and stereo image that basically shows the stereo behind the image of 2014 coronal mass ejection that we saw. So this actual data show that those big flares always come, I call it the trinity. It's a flare, coronal mass ejection, and energetic particle events, and they're all physically connected, the result of the same process. That's what in the schematically it is. So you have a flare, you have the formation, ejection of this huge cloud that propagates outward, and if we're lucky or unlucky, it can hit our Earth magnetosphere, so as the particles, particles can gain energy on this front shock, on the front of the shock, and basically create those energetic protons that can penetrate the Earth's atmosphere and cause some chemical changes that they're going to talk about. So this is basically the whole physics that basically is resulted from the combination of the 3 different processes. And of course, our sun, as we will show later, show the one of the least energetic processes, and still we feel them on Earth. So basically, this is opens up the question for different studies, from studies of how the coronal mass ejections get initiated, how this the magnetic structure loses equilibrium and gets out. So that's one project that we're studying, trying to study how to explain the stellar CMEs, what kind of parameters they should have, or whether we can be able to detect them or not. So we will discuss this question during the whole session in Athens at COSPAR meeting, just starting from 18th of this month. So, and then the second question is how the CMEs interact with the day side and night side of the magnetosphere. I'm going to talk about that a little bit later. It basically disturbs the magnetic field of our planet and other exoplanets. Can be much worse. Imagine that this magnetosphere is not at 1 AU, but at 0.05 AU, 20 times, which is a typical distance, 20, 30 times closer. So how it's going to affect the structure of the magnetic field, because this magnetic field opens up in the so-called polar cap, and the particles can penetrate in, okay, and then they ignite these showers. The showers starting the energetic protons with energy greater than 200 megaelectronvolts start to ignite, the chain of processes starting from kaons to pions to muons to electron-positron pairs, eventually forming the extensive ionization of the atmosphere. And this ionization of the atmosphere by itself causing the very interesting chemistry, forming the free radicals. And these free radicals can cause the new interesting molecules that we're going to discuss today. So therefore, as you can see, that's the whole physical-chemical environment. And I will show today that, that when I'm a theoretical astrophysicist, by my background, I never paid attention to chemistry. And only about 6-7 years ago, I realized that if we want to understand this environment, we need to be really very serious about chemistry, because chemistry regulates physics, and it creates the feedback to physics. And we never can understand those environments without understanding chemistry. Ion and neutral. So, okay, so now the next step is our sun. See that this is the quiet sun, this is the active sun. As you see, during active sun, you have more magnetic flux. So, this is you saw that in the optical band, this is the sun in the X-ray band. So you can see here, so during the active sun, every 11 years, that's called solar cycle, we have the sun in active phase, okay? those patches that I showed, that are basically the sites of the formation of flares, chiral match ejections that eventually cause energetic particles. So the one question that we asked recently, I said, okay, so can we, in the whole 11 years of data of observation of solar dynamic observatory, can we find one at least, or might be several examples of the when we have only one sunspot close to the equator, basically moving from one side to another side on otherwise quiet sun, okay? And what kind of signatures it creates. So basically, as you can imagine, so if you have a, if you have, let's say, the patch, the black patch right here. So I don't have a picture because it's not about that. It's just one slide. So you see the passage of the sunspot from here to here, from one side, from one edge to another edge. And as it does, in optical, you would imagine it blocks a certain part, right? It's darker. So therefore, you would imagine to have a dimming, right? That's exactly dimming that can also be created by exoplanet. You see the dimming here. So this is like 22 days of observations. Sun as a star, when we take and integrate all the sun in one pixel. So you see this is basically like a transit image, right? That's what normally see on exoplanets, or transit by the sunspot. But all other images, you can see it's enhancement. And we want to know how the enhancement in X-rays, in far UV emission, in different spectral lines, like helium-2, and X-ray, as you see the Hinori data, and ghost data, how it can be scaled with the size of a sunspot, and eventually with the magnetic flux. Okay, we don't have a good physical models. We do have some models, but we want to first develop this data-driven models, or empirical models. And that's basically the one study that we recently did to find that, to characterize what would be the percentage of, let's say, you can see here, the increase, by a factor of from 15 to about 30%, as you can see, depending on the wavelengths and the spectral line, extreme UV emission. You can have from, it was a pretty small, 240 millions of the solar hemisphere. Yeah, it's pretty small. It's like 0.2 the percent. But on stars, you can see sunspots all the way up to 10%. Okay? So we talk about much bigger sunspots. And so if we can characterize it well, then we can derive some relationship. So that the next study that we taken just recently, published only a couple of months ago. So we said, okay, so we observe different lines, on the sun forming from the chromosphere all the way to the corona. And they say, okay, so can we find the correlation of these lines if they're formed by the magnetic field eventually as a result of the atmospheric heating as a function of the magnetic flux? People have normally taken the studies looking at certain active regions here and here, finding the correlation at a much smaller scale. And then I asked myself a question. I said, well, if this flux is redistributed over the whole, the area of the sun, so then in average, I should have the total energy conservation, the total magnetic flux should be eventually be translated in into the energy of the emission of the spectral lines at different line, and we should expect a high correlation coefficient. And that's what you see here. So this is the correlation coefficient, 92.6% for the X-ray flux. Okay, so you can see that's as the sun was progressing from solar minimum, from smaller flux to solar maximum, and higher flux. So the correlation is pretty good. And then we put some solar-like stars, the young stars that only a few 100 million year old. They're also lie on that correlation. And then we did this to many other lines, like the extreme UV lines, the carbon-2 lines, far UV lines, and so eventually to 21 lines. And for all of them, we see very nice correlations, that show that the sun and stars, they have this data show that the universality in the magnetic heating. So this is the opens up the important topic to how we can characterize the stars just by measuring the magnetic flux, and we can do that by using magnetometers from Earth. We don't even need the missions, and then we can find those fluxes with the high degree of certainty. So this is the paper that basically specified that how the solar stellar studies you know, then you can see that how many co-authors, you know, that, and again, here, some of them are helio, some of them astroplanetary scientists and earth scientists, and also the prebiotic chemistry people who never heard about astrophysics or heliophysics before. How we can put it together, the unified picture, how the space weather, and the space weather is a term that basically unifies all those three processes that I talked about. Is the flares, is the coronal mass ejections propagating on top of the solar wind, of stellar winds, and energetic particles, all those disturbances between the star and the planet. If we identify those disturbances, characterize the fluxes, energy fluxes of those disturbances, magnetic field, then we will be better off to understand how the impact happens and what kind of physical models we need to develop. Because if we develop a beautiful model and don't have incredible inputs for these models, then the outputs also are going to be not going to be very relevant. So this is the image, the animation that shows the whole process of space weather from the beginning to the end. So you have the magnetic reconnection-driven instability that creates the flare loop here. Oh, sorry, flare loop. Then, sorry, yeah, and then ejected magnetic clouds that propagate up, as I said, with a few thousand times per second. And then it basically, collides with the magnetic shield of our planet, called the magnetosphere, or the region of magnetically dominated region around Earth. And depending on the direction of the magnetic field, if it's an anti-parallel direction, then magnetic reconnection will basically, erode the part of the flux. Magnetic flux create particles, and so particles will penetrate in, creating the aurora, and then actually squeeze the night side magnetosphere and form a secondary reconnection. So, creating the precipitation of electrons in, forming this beautiful aurora that can be observed from the International Space Station, exactly in the way that you can see here, and on Earth, let's say in Alaska. So the idea is that as from time to time you can see those events not from Alaska but also from Miami, because that happens when you see those big flare events. And so that's why it is important to find the conditions to understand, what impacts we expect during the big events. So again, so now going back, so the question that I want to ask about, well, can I understand our sun if I know so much now, about our sun? Can I go back 4 billion years ago, and what can I learn about our sun? So basically, by looking at that's the paper 2015 et al. They looked at 1, 2, 3, 4, 5 stellar clusters, and the stellar clusters are the clusters of stars forming at the same time. Okay, so they have different masses, and so as you can see here, they have different. This is X-ray luminosity of the star versus age. So you see this is the cluster corresponding like 30 million years, then like 100 million, then like 200 million, and about 1 billion. Okay, so and you can see that the X-ray emission flux varies by more than an order of magnitude. Why? For the stars in the same mass, it's because stars acquire different angular momentum at birth. Some of them are lucky, some of them less lucky, and of course the angular momentum drives the the generation magnetic field through magnetic dynamo, and the magnetic field, depending on how much you have, as I showed in my previous slide, the flux correlations will drive the different amount of X-ray emission and extreme UV emission. So the point is that some stars are so-called fast, rotating much faster, born rotating faster, so-called fast rotators, this blue, and some of them slow rotators. So now, at some point when at around the time when life started on Earth, this flux difference reduced, dramatically from order of magnitude maybe by a factor of 2. So, and we don't know whether our sun, and before that, the sun was when it was infant phase, that was saturated, and then was behaving in 3 different ways: fast, intermediate, and slow. And we want to understand what kind of sun we had before. At that time, around billion years, that's the time when the Earth acquired the secondary atmosphere, the atmosphere that we breathe in today. Okay, so and that's important, to understand why we're here, why the Earth still retained the atmosphere. And is that the kind of like extraordinary case, or is just typical case that what we should look from JWST? That's why it is important. And looks like that, I'm not going to talk about that, in our 2019 paper, we looked at the data from the sun, the data from the moon, from the lunar regolith, and the potassium and sodium data, and found that the best explanation of this data, Apollo data, is that our sun was a slow rotator. So it was pretty slow magnetically. I'm talking about weaker star compared to others of the same age. So this is what you see, a snapshot of our sun, like a sun star. So you see this red one is the rotationally modulated optical emission, which is specified by star spots. Imagine that it goes from like here from like 1%. That means that 1% to about 1.5, 2%. So meaning that this normal state. So as the sunspot passes through, so you would the object will experience, as you see from the plot, sun as a star, the dimming, right? So the dimming goes with the rotational modulation, with the rotation period of the star, and the blue one, the spikes are super flares. Flares that occur, you can see how many of them. This is 1 year, 2 years, 3 years, 4 years, 4 years of data with the cadence of 30 minutes per 1 point. So this is nice picture of in the life of one star, which is basically a very good analog of our young sun, to look what happened before and how we can use this data for the atmospheric modeling. Okay, and understand them from the physical standpoint. So that's exactly what the Kepler did. Many people say Kepler is only exoplanetary emission. No, Kepler is exoplanetary emission, and another not less important, I would say equally important, it's the discovery of superflares. Because if before Kepler we observe one flare, we write a paper in Astrophysical Journal. Now we observe 100 flares or 1,000 flares, how many of them, we write one paper. And we produce statistical studies, and we produce statistical correlation, it's a completely new milestone in astrophysics and exoplanetary science. So basically using this information about one of those stars that I showed and magnetic maps. So these magnetic maps are now available from the so-called magnetometers. Let's say the Canada, France, Hubble, Canada, France, Hawaii telescope. That measures the 3 components of the magnetic field. So we can reconstruct the magnetic field, large-scale magnetic fields of stars. So this is one of the closest stars, Kappa-1 Ceti, which actually resembles our sun, 4 billion years ago, rotating 3 times faster than our sun basically rotates today. It's a 750 million year old star. We have spectral polarimetry that gives us magnetic field, and this methodology called ZDI, Zeeman Doppler imaging, was already matured over the last 20-25 years, and especially when the signal to noise and spectral lines that used to derive the signals from Zeeman splitting, is high, so we can have the high fidelity magnetic maps. So the magnetic field is like 500 Gauss, which is a pretty strong field, the average field. And so we use the 3-dimensional magnetohydrodynamic model that is used in order to model our current sun. And so we ask a question about, say, that what is required, from a star in order to look at the star as a sun. Now I'm not talking about star as a sun as a star, but sun as a star. So now we have beautiful tools. You know, the NASA spent millions of dollars developing it because we can observe our sun in 3 dimensions. We can observe solar wind in 3 dimensions. So those sophisticated models should be able to reproduce, you know, those parameters at 1 AU. Can we use this, you know, to model those environments? The answer is yes, we can. First, because as I said, from empirical studies, there is a universality that allows us to assume that yes, young sun models and solar models can be treated from the same physical framework, because the empirical data show us. The second thing, we can derive important ingredients. So this is the one input parameter, magnetic field. The second input parameter is the, so let's not talk about that. This is the, from Hubble Space Telescope, we can derive, you know, same kind of data. This is the data, high resolution, this is the spectral light. So the high resolution oxygen-4 and silicon-4 forming at 50,000 kelvins in the upper chromosphere of stars. So our sun also shows those lines. And what's interesting about it, so you can see they're pretty broad. So they're broad, so that broad that they can be approximated not with one Gaussian profile that you would normally expect, you know, if it's a Doppler broadening, but with the second one, you see this, the broad one. So it shows that pretty strong wings, and the broadening is non-thermal, meaning that the broadening is not just a specification of the thermal motion of ions of oxygen-4 or silicon-4, but it shows Mach number 3 or 4. Okay, so that suggests that it's supersonic motions. But if it's a quiet sun or quiet stars, you cannot have that. That means that you were dealing with the magnetic processes like Alfvén waves. So moderated by Alfvén speed, which much greater, and that result that shows this the non-thermal broadening at the level of about 30-40 kilometers per second, which is with the line formation, you know, temperature sound speed only 7-8. Okay, so which suggests that we're dealing with Alfvén waves. So we use this data, you know, to reconstruct the Poynting flux in Alfvén waves as a boundary condition in order to create the corona of the star first, and then the stellar wind as extension of the corona. So this is basically the process. So so we start with the, you know, the solar model that applied to stars with those two conditions, the magnetic field and the Poynting flux, and then for basically form this, you know, this is the magnetic skeleton. Color shows the plasma pressure. Okay, the higher here, lower here. So you can see here a 3-dimensional image of the corona of the young sun, Kappa 130, in 2019 data, okay, in September. And then 11 months later, 2013 August. Look at that. So you can see that the magnetic field of the star, you know, transitions from the kind of like dipole-like field into the tilted dipole with the, you know, the lot of disorganized field, the quadrupole and octupole field. So we can see the first lesson that we learned, that the magnetic data together with simulations show that our sun and those active stars show, you know, very dynamic magnetic field, and the variation of the magnetic field is not years as we see here, but only months. Okay, at this point, it's only about a few months. So therefore, in order to understand it, we need to have a cooperative observations, Hubble observations with X-ray observations, because the one observation doesn't tell us a story. So this is the reconstruction of the solar wind 4 billion years ago, showing that the solar wind was 100 times, you know, stronger, I mean, mass loss rate I'm talking about, than we have today, with the average speed about 1,000 times per second. And that's important because we want to use this data in order to understand how this young solar wind from the young sun interacted with the early Earth magnetosphere. And this is the interaction of the slow wind with the fast wind creates so-called rotating interaction regions, which are shocks. Yeah, this is the orbit of Earth, the black one, and the red one is orbit of Venus. So this is basically the simulations that we're now doing. We're using this, you know, data that we acquired, three-dimensional data, in order to calculate the magnetospheric magnetospheric conditions of early Earth and Venus and Mars. So we discussed that in my paper published last year, but now we're doing more detailed calculations using this data. Another topic is the super flares. So they show those blue spikes, that's the super flares. We also model the super flares, using those magnetograms for the same star. So once we know the corona, now we use the corona of the star as a background conditions in order to start and study the loss of equilibrium of the star and the formation of those flux ropes. So imagine that you have the differential rotation of the star, and then as differential rotation persists, so that you start introducing non-potential field or electric currents, to the initially potential field, and you see that the field becomes twisted. At some point that it loses equilibrium. So this is from its side, and this is at the North Pole. Okay, and so you see this is the image, the simulation, 3D image simulation that creates the coronal mass ejection. So this you're looking at Earth and at the side. This is basically at some point when the field loses an equilibrium, it erupts, forming those huge halo-type events that we observe from time to time from our current sun. Okay, so this is the basically view of the sun from the North Pole. Okay, so and Earth is here somewhere. Okay, so next, so this is as the CME propagates from here, it interacts, and then see that I told you that we would expect that the strong perturbation of the Earth magnetosphere due to the interaction with the CME. So we're talking about 1.5 Earth radii. So you see the 70% of magnetic field opens up the polar cap, and so the next question we want to ask: well, now we have 70% of field opens, during those events for a couple of days, for 2 to 3 days. What's going to happen to the energetic particles? So this is the third point that we started to study. Well, this is the atmospheric escape that I probably will skip for now and move to the topic of the, propagation of coronal mass ejections forming shocks. And then when you have the shocks, you have the particle acceleration in the shock front. Particles go back and forth, and they statistically gain energy due to the Fermi-1 acceleration. And so we use the magnetohydrodynamic model together with the kinetic model called IPATH that is used to model the solar energetic particles to reproduce the stellar energetic particle events in a paper that was recently published in Science Advances a couple of months ago. So for associated with the solar super flare event. So this is the current sun. This is the young sun 4 billion years ago. This is the infant sun only 100 million years ago, 4.4 billion years ago. So we basically modeled 3 different environments and derived the spectra. So this is the spectra from our current sun, where we explain the statistical data from solar energetic particles, because firstly, if our model is credible, we need to understand the solar data, right, described, and then go to the more energetic events. So this is the stellar energetic events from the young sun, and the blue one from the infant sun. As you can see, the spectra of those events have become much flatter. So the spectra are much harder. So you have particles here only to like a couple of gigaelectron volts, here to 10 gigaelectron volts, up to 40 gigaelectron volts for the super flare associated SAP events. And that's very important for the later implications, because high energy particles propagate much deeper in the atmosphere and cause ionization. So this is basically the solar data that we can explain. And this is the data, from the young sun. This is the data from the infant suns, and this is the event 775, the one event that was particularly strong in the Earth's, recent past, 775 AD, only 1,300 years ago. Okay, and as you can see that, this is the current events, and that's a pretty, much, much stronger than anything was observed before, even stronger than, or the same order like you normally observe from the young sun. But it, of course, doesn't happen as frequently as you would observe it on the young sun, but still the same category. So when you look here, this is the spectrum of, the spectrum of the current sun, much, softer. This is the much harder spectrum. So now the question that you can ask, what this hard spectrum does to the Earth magnetosphere and atmosphere as the particle penetrate in. So this is the last topic that I want to discuss. So as particles penetrate in, they create the showers, as I was talking about, and those electrons that are produced, electrons and positrons, electrons produce the, the ionization. And so these electrons, they bump into the molecular nitrogen, carbon dioxide, methane, and water vapor. There's 4 major, gases. And these gases are CO2, H2O, and CH4. That's volcanic gases. Okay, so that's coming from the volcanic activity of our early Earth, and then 2 is the result of tectonic activity, the result of the subduction to the existence of tectonic plates. So basically, this was a typical, the chemical ingredients of the early Earth, and the N2 now. You can ask very simple questions. You know how much N2 you have in current atmosphere? It's a 78%. So the point is that N2 is the most geochemically stable molecule. It was 78% or 80% 4 billion years ago, because N2 doesn't talk to anybody, because the 2 atoms of nitrogen, they're bounded with the energy of 10 electron volts. And it's so hard to destroy those 2. The only way to do it is to apply non-thermal energy. It's lightning, or it's energetic particles that can basically, eventually thermalize and reach that condition to destroy. As soon as you destroy N2, CO2, CH4, and H2, you create those, those molecules, CO, CH, NH, NO, OH, and those ions. So if those guys, they don't talk to each other at the current temperatures, they not interact. So as they do not interact today. But as soon as you create those, they're highly interactive molecules. Through the number of reactions, they form interesting molecules like hydrogen cyanide. It's a poisonous molecule, but it's the molecule at the heart of the prebiotic chemistry. If you put 5 HCN together, then you create the adenine, which is the nucleobase, one of the major nucleobases in your RNA and DNA. As simple as that. So it's basically a couple of, the chains down in complexity, and you can form very interesting molecules that you need to explain. Why do we have RNA? How do we have DNA? To understand that, we want to know that how we can create the smaller building blocks as the precursors of those molecules. And turns out that, those molecules can be created. We see those HCN molecules in the interstellar clouds due to the result of the, photochemistry. Another molecule that's easy to create is formaldehyde, and then laughing gas, nitrous oxide. It's all a result of the same chemistry. See that I have only a few reactions. In our photochemical code, we have now about 300 reactions. But in our original code, we have only about 128 reactions, and where we found that nitrous oxide is a potent greenhouse gas, 300 times more potent than the carbon dioxide. And that can help to resolve the Feynman-Tensance paradox. I said that the Earth was supposed to be an icy ball because the sun was 25%, less brighter bolometrically than it's today. And so you need some kind of a global warming, extremely efficient warming in a greenhouse gas in order to increase the temperature to the level to make sure that the water standing bodies of liquid water exist on the planet. And the second, at the same time, you have the precursor molecules of life. So you can have the chemical paradox of life resolving with the atmospheric paradox, because without water, you cannot have any, the polymerization of those molecules. So this is the whole process, how it works. And then the experiments that we started in Japan also shows that we can actually explain theoretical models, formation of N2O molecules, and formation of HCN. It's the experiments at the grounds of the Yokohama National University over the last 2 years. Yes, and so this is our climate model that show that the temperature of Earth can be like 5.2 degrees average temperature, which shows that with N2O that we produce, we can explain the Feinstein-Sas paradox using the three-dimensional climate model. And so that I'm going to end with the one case that what we look at different conditions. For instance, we find that in the paper that's submitting now about TRAPPIST-1. TRAPPIST-1, unfortunately, doesn't have promising conditions for habitability and even for the existence of atmospheres, even thinner atmospheres. But there is one interesting planet that we recently discovered. I was a co-author of that paper, TOI 700d, which is within the habitable zone, around the planet. TOI, it's the star, and you see that at 0.16 AU, very far away. So this is the extremely inactive star. So the extreme UV emission flux is very low. So we did the modeling to show that, for this star, because it's pretty young, it might be a little bit older than 1 billion years old star. This star can have a thick atmosphere, and it resembles the example of the young sun. And the early Earth conditions, especially for this planet. Okay, so this planet can be habitable. So I wasn't actually optimistic enough, but this might be the first case. So James Webb will start its first operations on July 12th. It's just about 4 days. But we'll observe TRAPPIST-1 very soon this year, and we will see that whether our predictions are correct. And we will look for the TOI 700d also with James Webb to check the spectral signatures. This is the spectral signature conditions, transition spectrum that we created using this climate code with my collaborators from GIS. It's Goddard Institute for Space Sciences. So this is different bands that, this is the albedo and transit depths. So what you expect from transit observations. So my conclusions are that, the space weather is very, very important because, I didn't talk about the atmospheric escape, but, in my pretty, short talk, I wanted to basically, pay attention to the conditions surrounding our Earth, current Earth. The early Earth show that SCPs can supply free energy to start the chain of reactive chemistry, because life, as we know it, is the system with chemical disequilibrium. So in order to create the chemical, the big molecule can be considered as a miracle of life, as a miracle, actually, if you don't do anything in the equilibrium. You would never expect formation of big molecules out of nothing. But if you push those small molecules continuously with supplying free energy, then you, as experiments also show together with the model, then you can form, from atoms, the simple molecules, and the simple molecules start to interact, building bigger and bigger molecules, and when they precipitate to the surface and interact with the minerals and water, they can create huge molecules. We talk about up to 100 atoms. So, and that's the paper that was recently published by my co-author Stephen Benner, who is the experimental prebiotic chemist. So yeah, and so we discovered the first candidate for early Earth, and so now multi-mission Hubble, XMM, Newton, and NICER test of International Observing Program is in progress in order to specify conditions of the exoplanetary systems that can provide promising conditions for habitability. That includes the TOI 700d. Thank you for attention.